Okay, I guess we could probably just get started then. I'll just introduce you guys. So today we have Romana Boiger, who's a tenure track scientist at PSI, and also Rob Modini, who's a senior scientist also at PSI. And today they're going to be talking about using invertible neural networks for retrieval of aerosol properties from different measurements. So without further ado, you guys can present for about 40 minutes. And then at the end, with whatever time we have left, we could answer questions or have whatever discussions. So take it away.
Thanks a lot, Joe. So yeah, as Joe mentioned, we'll talk about our recent paper, which was on invertible neural networks. Since we're sitting in Switzerland, I thought briefly just to give a picture of where we are, as you may not have heard of the Paul Scherrer Institute. So it's a federal research institute. We're based in the north of Switzerland, like really just on the border with Germany. The institute's mostly known for like its large scale facilities. So there's a synchrotron light source and a free electron laser. But we also have a lot of computing and modeling going on and a little bit of environmental research. And that's the part that I'm involved in. So I come from the Laboratory of Atmospheric Chemistry. So this is a different part of the institute to where Romana is coming from. So when we started this collaboration, she was in the Laboratory for Simulation and Modeling. She's now moved to the Laboratory of Waste Management. And it came about because we saw a presentation from the modeling group on these invertible neural networks, but it was applied to a different inverse problem, which was like the optimization of a particle accelerator operation or something like this. And we thought this is an interesting solution, could potentially apply to this inverse problem that we have in aerosol science. And so we started the collaboration and we'll present the results today. Yeah, Romana and I are presenting, but there's many others involved in the project, and this is just one sub-project in a much broader range of research activities. And so just to highlight our colleagues below who work with us. So yeah, as I said on the previous slide, I'm the problem part of this relationship, and Romana is the solution. So I get to introduce the general topic and introduce the inverse problem that we hope to solve. And then Romana will take over and talk about the invertible neural networks and the results that we got. But yeah, the focus is on atmospheric aerosols. That's what we're interested in. And so I like to start with this global portrait of atmospheric aerosols, which is just a picture of them on one particular day of the year in 2018. And I like this picture because it shows kind of the complexity of what we're trying to study when it comes to aerosols in the atmosphere. And in particular, it shows like the extremely strong spatial variation. Like for example, on any particular day, if we look at Africa, for example, the north of the continent we'll have very strong loadings of dust coming from the Sahara, whereas the picture in the south of the continent can be completely different. In this case, there was a lot of black carbon coming from biomass burning. And yeah, so we have this extremely strong spatial variability, which makes them a very challenging thing to study. And we need to know this spatial variability because obviously if we think about aerosols over the ocean versus these black carbon aerosols or the dust, then the environmental impacts are going to be very different. For example, like if we think of their climate impacts, this highly absorbing smoke is going to be very different to aerosols over the ocean. So we need to be able to model and understand this. What gets even more interesting in modern day times is we kind of want to do this in real time now, which is even trickier. And a good example last weekend here in Europe, We occasionally have these episodes where dust from the Sahara comes up and travels over Europe. And what happens when this occurs is the weather models are not taking account of this dust at the moment. And so we have large forecast errors in the weather forecast because of this. This also affects things like solar energy production and so on. And so as these things become more important, there's a push to try and get this global distribution in kind of near real time. How can we do that? Okay, so basically we need a huge infrastructure to be able to provide this global picture. So obviously we need a model to be able to track aerosols everywhere around the globe over time. But to make sure that that model is realistic and reasonable, we need to assimilate observations into it to make sure that the models are giving us reasonable pictures of the global distribution. And so I like this schematic, which comes from a very recent review from Ralph Kahn. And he talks about basically the three pillars that we need. So as well as the models, we need two types of observations. The satellite observations, but also observations from within the atmosphere. The satellites are important because they provide very broad coverage in space and time, but the problem is the measurements are not very detailed, and so we need to supplement those with suborbital measurements or measurements from within the atmosphere. So this is the part that we're mostly focused on in our research, is on the observation side. And traditionally, we come from more the within the atmosphere part. And so in particular, we operate measurement networks. For example, we operate a measurement station on the Jungfraujoch, which is a famous mountain here in Switzerland. And we've been taking measurements there for continuous aerosol measurements now for the last 25 years. More recently, we've started to move into this issue of how we can then combine such observations with satellite observations. And there's many details that can be covered here. One thing I'll point out today is that amongst all these different types of observations, aerosol light scattering is a key physical process. All right, and so that's an important basis for many of these observations that are feeding into this system. Okay, to show that in a bit more detail here. So we have many different types of sensors that are probing our atmosphere, which are based on this principle of measuring the light that is scattered from aerosol particles. And the important thing to point out is that that scattered light depends on the properties of the underlying aerosol. So, for example, how much of the aerosol is present, its size, the refractive indices of the particles that are present, and their shape. So if we then take these measurements of light scattering in the atmosphere, the trick is we then want to apply inversion algorithms, or we want to try to retrieve information about the underlying aerosol properties. So this process is the same whether it's done using a satellite remote sensor or ground-based remote sensing instruments or in situ measurements that are taking measurements of light scattering within the atmosphere. So in all these cases, we want to use inversion algorithms to try to retrieve information about the aerosol. So what are some of the approaches that are used to invert measurements of scattered light? The first one, and the one that's probably used most commonly in remote sensing at the moment, is pre-computed lookup tables. So here we can create tables where we take different sets of aerosol properties and pre-compute different like properties of the light, and then we could try and match our measurement to these tables and try to retrieve some information. The advantage of these methods is that they're very fast. This is a quick process, So when we're talking about the very large volumes of data that come from satellites and different networks, this can be done in near real time. The disadvantage of it is you're necessarily simplifying and discretizing your solution space. And so this can lead to some inaccuracies. The next method that's been applied, which in order to improve the accuracy, is to do a full physics-based retrieval. And in this case, the key point is we need a forward model of the underlying physics. So the classic example is me theory, okay, where we assume that we have spherical particles, and then we're able to simulate the scattered light from these particles. Then we can use different iterative solvers in order to solve this inverse problem, and this can be done very accurately. And so a current state-of-the-art example is the GRASP algorithm. This stands for the Generalized Retrieval of Aerosol and Surface Properties. This is a very versatile algorithm, so you can put in many different types of data, whether it's from remote sensing instruments or in situ instruments, and you can then solve this iterative process and as an output have some properties of the aerosol and also of the underlying surface of the Earth. And these things work really well. They can be very accurate, but we then come up with computational speed problems. So when we're based on me theory and we're making a simplification that we have spherical particles, then this can be done relatively quickly. But if we want to simulate more realistic aerosols with more complex shapes, then speed very quickly becomes a big problem. So more recently, where a lot of research has started to develop is whether we can then use machine learning-based models to solve this inversion process. And the hope with such models is that once they're trained, they're then going to be able to be operated much more quickly than full physics-based retrievals, and hopefully with similar levels of accuracy. But this is still a question whether this is going to, how successful these approaches are going to be. And I also mentioned it doesn't need to be either or. So very likely it's probably going to be a combination of different approaches that ends up being the most effective way to solve these inverse problems. Coming back a bit towards our research at PSI, thinking about these different inversion products, the question we like to ask is how can we then validate the retrievals? And so if we're thinking in terms of a remote sensing retrieval, what we're actually doing there is we're probing a column of the atmosphere. So for example, a satellite is looking at some of the light scattered through a column of the atmosphere. If we then perform a retrieval on that measurement, what we're retrieving is some kind of average aerosol properties throughout that column. The difficulty with this is it's hard to independently measure such average properties. And so it's hard to validate such retrievals. For example, we could take a plane and try to fly it through the same column, but this is going to be a very costly thing to do. And we're always going to have a question, do the measurements match up precisely? So validation is kind of a very tricky thing. One approach that we've tried to take in order to validate these different retrievals is to take it back to the laboratory. And so in particular, we've developed a prototype laboratory-based instrument that allows us to perform in situ light scattering measurements. So in this case, what we're doing is we're drawing aerosol from the atmosphere into an instrument, which is known as a polar nephelometer, and we're shining laser light onto that aerosol sample and then measuring the distribution of the scattered light coming off that. The idea behind this is that because we're in a laboratory, we can then use very well-controlled and defined aerosols, and we can also have co-located independent measurements of the properties of that aerosol. so that we can validate the inversion. And so, yeah, this is a schematic and a picture of the instrument that we're using at the moment. And the two things that we measure are what's known as the scattering phase function, which is the angular distribution of scattered light coming off that aerosol sample. And we also measure the polarized phase function. And so this is a ratio of two different polarizations of that scattered light intensity. And so this is the measurement data that we're dealing with. If we then want to test a validation, or if we want to validate an inversion, sorry, how can we do this? So we can set up an experiment where we have a particular aerosol with well-defined physical properties. So a well-defined size distribution, shape, and refractive index. We can put it into our polar nephelometer. We can measure the phase function and the polarized phase function, and then we can input those measurements into an inversion algorithm and compare the retrieval results with independently measured values or known values. And so these are the type of experiments that we've been doing. And we've just started to get our first results from this process. And so just to show some examples here. So if we start, first of all, with spherical test aerosols, so spherical particles, which are quite simple to model, then we can demonstrate that we can obtain accurate retrievals using the grasp algorithm. So there's a lot of detail on this bottommost plot, but the main thing to point out is that the independent measurements or the literature values are in black and gray, and different types of grasp retrievals in the blue or the red. And we can demonstrate that we're able to retrieve the aerosol size distribution and the refractive index, both the real and the imaginary part, with good accuracy. This is all well and good, but if we then take the same retrieval method, which is based on me theory, so assuming that we have spherical aerosols, and if we then apply it to aerosols that we know are not spherical, for example, these fractal shapes, we see that the inversion no longer works well, which is as expected. It's relying on an assumption that we have spherical particles. So what this means is that we need to move to more complex optical models in order to be able to simulate such types of particles, which again brings up the problem of computation speed, because the inversion works relatively quickly if it's based on me theory, but if we're using more complex models, then the inversion starts to slow down. Which brings us to the research questions of this particular project. And so given this problem, we then thought, can we develop an accurate and fast machine learning approach that's going to solve this inverse problem of aerosol light scattering? That's our first research question. We then want to see, is there a speed benefit from using such a model? And how do the results compare to physics-based retrievals like GRASP? And also, how do the results compare to independent real measurements? So they're the research questions. I now hand over to Romana, and she'll talk about the paper and our results.
Okay, so thanks a lot. So to answer these research questions, let us first put this in a bit more mathematical framework, our whole problem. So let's say we have our input, our cause, our aerosol properties that we will denote by X, and solving the forward problem, so retrieving our measurements, is then just applying some function f of x is equal to y. And the inverse problem, so going from the measurements back to our aerosol properties, would then be applying something like the inverse function. And from a mathematical point of view, the inverse problem is more often harder to solve than the forward problem. And the reason lies in the ill-postedness. which is here defined according to Hadamard. And inverse problems are ill-posed because there either exists no solution, the solution is not unique, or small perturbations in the data can lead to large errors in the solution. And that is mainly the case if we deal with measurement data. But nevertheless, we have ways to solve inverse problems. So there are different solution approaches. So there's this classical approach using regularization methods, meaning that we solve some optimization problem where we use the regularization term here. There is the Bayesian approach where we use random numbers and probability functions. And the latest approach, which developed quite fast over the last years, was the machine learning approach, like, for example, using neural networks that approximate either the forward function f or the inverse function. And well, the big disadvantage of the first two approaches is that we need a lot of knowledge and that they can be computationally very expensive. Whereas for the machine learning approach, we do not need any prior knowledge, but we need, of course, some data. But once our models are trained, we need little computational effort. And so the idea here was also to use machine learning because then we get a fast and accurate solution to our aerosol property retrieval. And in this case, our goal was to not only solve the inverse problem, but to also have a model for the forward problem. And there are different machine learning architectures, especially neural network architectures, that can do exactly that. So solving the forwards and the inverse model at the same time, like, for example, autoencoders. And so, but we decided to use those invertible neural networks that were introduced by Arizona in 2019. And so how do those invertible neural networks work? So maybe let's start by introducing again forward neural networks, which you might all be familiar with. So we have here our input layer, we have different hidden layers that are densely connected, meaning each neuron is connected with each neuron of the following layer, and we have some output layer. And with this kind of architecture, we can in principle approximate any function due to the universal approximation theorem. And we learn the weights and the biases within the network by optimizing such a cost function, which compares the predicted and the true output. So this is how normal feed-forward neural networks work. Invertible neural networks work a bit different. So we have, again, our input. And for the hidden layers, here we have some so-called affine coupling blocks and permutation layers. And those are the those affine coupling blocks are the most important parts of this invertible neural networks because they guarantee us in the end the invertibility. And this is how they look like. So we have here our input that is split up into two parts, U1 and U2. And they are connected via some mathematical expressions like exponential function, multiplication, summation, but also these functions s and t. And in the end, we get some output. So here you see the mathematical formula. And S1 and T1 and S2 and T2, those are neural networks themselves. And due to this special structure, we can compute the inverse analytically. So here we have the formulas. And yeah, so this is basically the trick behind those invertible neural networks. The permutation layers in between, they guarantee us that we do not split up the input always in the same way. And what we need that the invertibility really works is we need to have input and output to be the same dimension. So we need to add some padding variables either on the input or output side. And on the output side, we also have such a latent space that accounts in principle for any information that is in the input, but is not shown or not visible in the output. And now the last function is a bit more complicated than we had before. So first of all, we have again the same term as here. So we compared the true with the predicted output, but then we also want to compare the true and the predicted input. We have here some reconstruction loss. So we give the true input, compute the forward model, and then again the inverse model, and compare if we get again something similar to the true input. Here, this artificial loss terms ensure us that not much information is embedded in the padding variables, and this last term makes sure that our latent space follows a prescribed distribution. And with such a neural network architecture, we are now able to solve the forward and the inverse problem at the same time by only training one neural network. And this is how we did it then for our problem from aerosol physics. So the first step in our methodology was to compute the training data set. So we chose some aerosol properties within certain ranges. We used then the physics-based model to create our simulated measurements. And we used the properties and the measurements for training our neural networks. So in total, we had 100,000 data points where we used 80% for training and validation and 20% for testing. And once our network was trained, we can then use it for prediction. So we can either give the aerosol properties and get some predicted measurements, or we can give it some measurements and it will retrieve the aerosol properties. And this is how our data set looked like. So we assumed that we have a monomodal spherical pure component aerosols with a size distribution consisting of some volume, radius, and geometric standard deviation, and a refractive index for 3 different wavelengths. This was our input, and the output were the simulated laboratory in situ measurements, so consisting of the scattering phase function and the polarized phase function, where we have 1 data point per angle. Okay, and yeah, here are the results. So the first step to get good results was to do a data pre-processing. So for the scattering phase function, we needed to apply the logarithmic function. And then for both the scattering and the polarized phase function, we used the standard scalar. So this was really a crucial step in order to get good results with the neural network. And yeah, here is the result, first of all, for the forward model. So we get an R² value, this coefficient of determination of 0.997, where 1 is the best we can get. So this is already quite good. And the relative error of the scattering phase function is 1.5%, and the absolute error 0.06. So both lie below the expected measurement device errors. And for the inverse model, we get an R² value of 0.993, which is also quite close to 1. And here in this table, you see for the aerosol properties, the absolute error in the middle, and below for comparison, the weighted mean absolute percentage error, which is for all of them below 1.5%. And here you see a qualitative representation. So for different wavelengths, you see the scattering phase function and the polarized phase function, and here the size distribution. And you can hardly see the blue lines, so the true test functions behind, just because our fit was really good. Although one already sees here that for example, one sees that our predictions are a bit noisy, but that comes from the fact how we chose to model in the end, our data set. So we really took one data point per angle and not a smooth function. And then we further played around a bit with our aerosol data set. So we wanted to make it more similar to real measurements. Therefore, we looked at cases where one or two of the wavelengths are missing. And we also considered the case where we would only have the scattering phase function available or the polarized phase function. And in addition, we removed some angles at the beginning, the end, and in the middle, because with our measurement device, we cannot measure at those angles. And here you see the results for these different showcases. So on the y-axis, we have the R² value, and on the x-axis, you have the different wavelength combinations. So for one wavelength here on the left, a combination of two wavelengths, and here 3 wavelengths on the right. And the colors, so red are just the polarized phase functions, blue just the scattering phase function, green a combination of both, and brown is where we have everything available. So also all the angles. And we see here, as one would expect, that for the forward model, it of course doesn't make a big difference. But for the inverse model, the situation is different. So here you see the absolute errors for the different aerosol properties. And we can clearly see, if we look at the red circles, that we cannot predict the volume if we just have the polarized phase function, which also makes sense from the definition of the polarized phase function. And we also see that it is harder to detect the radius and the real part of the refractive index if we have just given the polarized phase function. And what we also see, which might also not be very surprising, is that the best results can be achieved if we have both functions available, and the more wavelengths we have, the better the results are. Yes. So far I showed you the results which we had in the paper. We also did it then for a bit more complicated case where we had a bimodal aerosol distribution, but there the results looked quite similar. That's why I will not show it here. Instead, I want to show a more recent result where we looked at the performance of such networks for real measurements, which is not yet published. So here you see 4 different measurements. So the dark blue solid lines are the measurement data. And here we first wanted to apply the network we had in the paper, but this was not really possible because the range of the aerosol properties that we measured here was outside the training range we used for training our neural networks. So we needed to train new neural networks, and we played around with different aerosol property ranges, but also with different data set sizes. And in addition to training the invertible neural network, we also trained neural networks that approximate only the inverse function. And this is what you can see here, because they give a bit of a better results. And to be able to approximate really the inverse direction, the trick was to add, in addition to such a feed-forward neural network, add a Gaussian noise layer. So that was a crucial point. And so what you can see here now, so that the dark blue dotted lines are then the retrievals from with our forward neural network. And you see that, for example, for this case and this case, they match quite well, but here for measurement 6 and 8, there is still some room for improvement. And yeah, we are somehow still working on improving that. So to summarize now and answer some of the research questions. So yes, we were able to develop a machine learning model that solved the inverse and forward problem for aerosol light scattering. We did it with invertible neural networks, but we did it also with forward neural networks and Gaussian noise layers. We also saw, by using the machine learning models, we saw an increase in speed. It compared to GRASP, it was 1,000 times faster. And it actually showed quite similar results, like physics-based retrievals. And we also saw that we can, if we have the right models, we are able to retrieve the aerosol properties from real measurements. Yeah, and as mentioned, most of the work is published in this publication. And with that, I will hand over to Rob again, because he will show you some of the currently ongoing work of his laboratory. So.
Yeah, so very quickly, just 2 slides to kind of finish off with next steps and kind of future outlook. So yeah, that first part of the project worked really well, and we could kind of demonstrate successful proof of concept with this approach, which was really cool. And so now we think to move beyond spherical shapes, where the light scattering problem is already pretty well defined, to more complex particle shapes that are more, perhaps more representative of the different types of shaped aerosol particles we can find in the atmosphere. And so this is where our current efforts are focused, and this involves performing simulations of these light scattering distributions for different shaped aerosols. We are using a multiple sphere T matrix model to perform these calculations, which is takes a lot more time than the ME calculations we were doing for the spherical part of the project. At the same time, we're measuring these aerosols like this in the laboratory and starting to build up our training data set so that we'll be able to train some new invertible neural networks using these more complex aerosol models. That's the future outlook there. Also very briefly mentioned something completely different. So this was kind of the first collaboration of its kind that we did at PSI, and we think it worked pretty well. And so then we thought, Romana and I thought about what are some other problems that we could try to combine some of her machine learning expertise with some of our aerosol data sets. And one idea we came up with was using the measurements we collected our research station at Jungfraujoch. So here's a picture of the research station. So this is where we have over 25 years of continuous measurements now. And one big issue we get up there is we're conducting these measurements, and then we have these dust events that occur. And you can see in the picture here in the top right corner, looking down the glacier. So on a clear day, this is what it normally looks like, quite stunning. After the passage of a Saharan dust event, you'll see it's very yellow and kind of yellow snow and ice where the dust is deposited. And for these type of strong events, it's obviously very obvious when a dust event has occurred. But there's many weaker events which are much harder to predict using the measurements or any other type of indicator, actually. And so we're now going back over our old measurements and applying different types of models to try and identify these states, and very interestingly using some unsupervised methods to see if we can get a model that does a better job of picking out these dust events than we've been able to do manually as humans. And so this is something that Romana and I started, but Romana has moved on now to another laboratory. But we have a master's student, Andrew Zia, who's working with us now. And yeah, I don't have any results to show yet, but just to present it as an example of how we try to combine our in situ measurements with some of the data science and machine learning activities ongoing at PSI. Okay, so yeah, thank you very much for listening and for your attention. And if you have any questions, we're happy to answer them.
Great, thank you so much. Let's see if there's any questions in the chat. Yeah, maybe if there's any questions from online first. Jatan, yeah, go ahead.
Thanks for the great talk. I had a question for Romana. I think I missed your slide about like how the scaling is really important. Maybe could you like walk us through why, or like, you know, what was important in that slide, or like in general, how you found that pre-processing the data affects the results?
Yeah. Here is the slide. So I mean, here you can already see.
We cannot see your slides. Yeah.
Sorry. I will. No, it should be possible. Right?
Yep.
Now you should see it. Yeah.
Yep.
So here you see, for example, the phase function, the scattering phase function. You already see here from the plot that the functions are not really distinguishable. And so if I take the logarithm already from those functions, then one can distinguish all the functions much better. So that's the first point in doing the pre-processing. And the other thing is, if you look now at the scale, so if I take the logarithm, I'm somewhere between -14 and -26 for the scattering phase functions. But for the polarized phase functions, I'm somewhere between -1 and 1. So the ranges are quite different, or not quite, but they are different. And therefore, we then decided to do another scaling step. In this case, we took the standard scaler to just have all the functions at the same scale. And that makes it in general better for neural networks and easier for training. So we also tried it without doing all those steps, but the results were much worse.
Yeah, and no, this is, and I'm wondering if you did like in some sense consistency with like the physics, because here, like, yeah, there's a numerical reason, I'm sure, but like, yeah, the sensitivity to log of the polarization, like, does it have any physical meaning, or no, this is just a convenient numerical tool?
To taking the logarithm, I think it's quite standard to do it for scattering measurements.
Yeah. No, I believe.
Yeah.
No, I think this is great, and I feel like, you know, this is one of those happy accidents that work. But I'm just wondering, like, if this means anything in terms of, or maybe not. Maybe it doesn't have to. Just
I don't know.
Yeah.
What it means in terms of physics.
Yeah, there probably would be if you, I mean, potentially, but yeah, I mean, you would need to go through the equations of me theory and see if there is some physical basis behind doing something like that. We didn't do that, but it worked. Yeah.
No, awesome. This is great. Thank you.
Can I ask?
Oh yeah.
Romana, I'm wondering if you could elaborate on the Gaussian noise layer step, and like what did that help you with, and why was that so critical for the observations?
In principle, when you want to solve an inverse problem, you have this problem of ill-postness. And so if you would use just a feed-forward neural network, you without any tweaking, then you would get into trouble if you enter some noisy data, because then the results can be quite different to what they should be. And by adding such a Gaussian noise layer, what you in principle do is you add some noise to your input already. And that makes it in general much more stable. So in the end, you do some kind of regularization. And then that helps a lot to make a network more stable.
Estimate error at all?
Sorry?
Or can you use that to estimate like uncertainty in your retrieval?
You mean if I can use the Gaussian noise layer to estimate some
Yeah, so
no, I don't think so. No, it's in principle just an additional layer in your network for estimating really the uncertainty. One would use some uncertainty quantification method. So one would need really to propagate some noise at the beginning.
Does anyone else have questions online? I have one question actually. So for someone who's not like really familiar with the invertible neural networks, the way you from this presentation, it kind of seems like almost like a silver bullet solution. Like you're able to get two from one, like the forward and the inverse. So what potential pitfalls are there, like from your experience, and when would you like resort back to using like the more classical approach or Bayesian approach?
I mean, if you know all the physics behind your problem and calculating with all the physics, you know the forward problem is not really computationally expensive, then I would go with your just physics-based model and use some classical approach. On the other hand, if you already have a lot of measurements, for example, then of course it's worth trying something like an invertible neural network. But I think somehow a problem with the invertible neural network is that you have a lot of hyperparameters that you can choose, because it's not clear how many of those affine coupling blocks you will need, how many of the permutation layers, and also how you choose the neural networks in between your blocks. I mean, we made our problem easier because we decided to use one neural network for all the S and T, but in principle you could choose 4 different ones, and then you get a lot of hyperparameters. And that makes it computationally expensive to train such neural networks, or to find the right hyperparameters to train it.
I see.
Yeah, and I can also say, like, we hit the limit a bit. I mean, this was using, so the range of aerosol parameters that we trained this network over initially was quite narrow. And we then had a thought, okay, it would be great if we made this very broad so that we wouldn't have to train different networks for different types of situations and measurements and stuff like this. And I think at this point, yeah, we started to approach the limit of like what we could achieve with the invertible neural network without doing a full optimization of all the hyperparameters and so on. And then at some point we reverted back to a standard forward neural network to do this. Yeah, so there was that limit that we got to eventually.
I see. Any final questions? If not, I have one more question if you guys have time. So Do you think there's any implication for invertible neural networks for like maybe explainability? In terms of the physics, like if there's kind of like more unknown physics, or if you're comparing different physical models, like I'm thinking in the context of like microphysics, or like cloud microphysics, for example, where the physics are kind of unknown or uncertain. So do you think invertible neural networks have any kind of implication for that explainability portion? Or I don't know if you have any thoughts on that. If not, that's totally fine.
A good question. I mean, maybe you want to say something,
No,
Romana?
no, I have not really thought about it. So
Yeah, I mean,
Okay, no worries.
I can't speak from the kind of machine learning point of view. I mean, one step we tried to take was like, which as a next step was to try to, so for example, if we start with the physics-based model and we input a phase function that corresponds to like a more complex aerosol, for example, like a bimodal aerosol, and we only try to retrieve a monomodal solution, then we know that this physics-based model is going to give us some average distribution that approximates this bimodal size distribution. And so then the next set of games that we wanted to kind of play was what does the neural network do in this case when it's giving some kind of effective size distribution or effective set of refractive indices or so on. And it seemed to work pretty well, actually. Like it gave like kind of like a physically reasonable result. Whether that's something that could be explored and tweaked to try to like gain some insight into the underlying physics for a problem like cloud microphysics where you don't have access to that, maybe. But yeah, we didn't fully explore that yet.
Cool, thank you. If there aren't any questions, then I guess we can conclude. And thank you, Romana and Rob, for your time. And yeah, take care.
Yeah, thanks a lot, guys.
yeah, thank you for inviting us.
Yeah, bye.